I would like that in your class too, the existing groups that you have already, you would meet, all of those groups would meet and then discuss from chapter 0 to chapter 4, because that is where your exams will be coming from. So from chapter 0 to chapter 4, what you have to do in the group would be to solve all the questions. Yeah, solve all the worked examples, just solve all of them together. Then you would solve at the end of the pages from 0. So at the end of each chapter, there are worked examples there. So at the end of each chapter, you're going to solve all the worked examples. Not all, you're going to choose 3, a minimum of 3. You can choose more, but my minimum is 3. Then you solve this minimum of 3 at the end of each chapter and present it as your assignment. Present it as your assignment. Now, so you're going to present 2 things, 2 items to me. Number 1, you're going to present a report, right? So a report of what you guys discussed when you met. I'm going to present number 1, a report. So the report is actually a minute. You're going to write minute on what you discussed when you met. Everything that you talked about, everything you discussed when you guys met, you are going to write about it.
Okay, see.
Whatever happened, the time your group members came, so you're going to sign an attendance sheet so that the attendance sheet will have the names, the index number, and if possible, the telephone numbers, so I can call those who are not coming. Then the time they came, time of arrival, and then you sign. So, and you need to make sure that you're not lying on that sheet there. So if you start the meeting at 5, the person who is the secretary should write, meeting started at 5, meeting ended at 8. So just take note of all of those things. Meeting start time, meeting end time. Then you're going to so meeting start time, meeting end time. And then what you guys discussed in the meeting, you would put everything down and solve all the worked examples inside that meeting minute for submission. Then you will separately submit your assignments at the end of each chapter in groups for submission. So that is so 2 things that I want from you: your meeting reports, then your assignments, which is 3 at least, so more than, greater than, or equal to 3 questions at the end of each chapter. So kindly convey this information to your class members, those that are not already on the call, so that they would all be on the same page and we can all work together. Is that right?
Yes, sir.
Okay, great. Rahana is not on the call. Yes, Steven.
When are we starting it?
No, you have to start as soon as possible. So for the B's, when I met them Tuesday, I gave them Friday today as the deadline for submission, and they begged for an extension. So I considered them to Tuesday. And I know that this work is plenty. If you really want to sit and wait, you won't be able to do it. So let's say that for you, your submission deadline on this work should be Wednesday. And you have to start early on. You have to meet, your group members have to meet. You have to meet at least 2 hours. 2 hours and 2 hours and 3 days. In fact, 2 hours. If you meet 2 hours for 3 days, you will still not be able to finish it. To be honest with you, so you guys really, really, really have to start meeting because there's plenty. What we've done so far from group 0, from week 0 to week 4, is a lot, and I don't think you can really finish everything if you don't meet almost every day. Now, the purpose for this group work is to teach you that engineering is not an individual solo job. Engineering is a group work, and you need to be able to develop the skills of working with people. Some people don't know how to work with groups at all. Some people are very, 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 very lousy when it comes to working in groups because they feel superior. They feel like they are excessively intelligent than everyone. So I'm not able to work well with people. And when you go through it, so when you go to the industry, those people, they really hardly rise. You can't rise when you're like that. You just can't rise. Nobody would work with you. You'll be an island. You'll be a lonely man. And no matter how intelligent you are, you will not be able to succeed in the industry. So I want you guys to use this opportunity. See, like I always tell you, I'm not teaching you for exams. At times you guys forget that. I'm not teaching you because I want to just give you an exam and you pass. No. The goal is not the exams. You can get an A in my class and it still means nothing if you can't go to the industry and work. So it means nothing if you can't go to the industry and work. So guys, I really encourage all of you to take your perspective. Most of the times, you students come to the university and your perspective is, oh, we need to score A, we need to, no, here. Those things are just, it's a lousy thing. Don't let your goal be on, I want to get A. No, here. It's not important at all. Yes, A is good. Getting the first class is good. But you should think about the fact that you'll be going to the industry to work. And what will you have in your mind that you're going to work with? In fact, all the teaching we are teaching you is so that when you go to the industry, you can get something to work with. So take your perspective away from exams. That is why if you look at me, I always tell you whatever I'm teaching you is practical. It is about what you're going to use in the industry. So some of you that are still thinking or exam centric, I really want you guys to take your perspective off and then refresh your mind on the right path. Build the skills you need to survive in the industry today. Group works, getting along with people, and then contributing to whatever discussion is going on in the industry. That is what gets you ahead when you get into the industry. Please, is that right?
Yes.
Great. So,
Yes.
great. That's awesome. So that's the goal of the group assignment. And the other,
Sir,
unless yes,
talking about when we meet, we should write the time we started and the ending time.
yes.
So
So
let's
that's
say
what we call minute.
yeah,
So I'm
like
going to write
anytime
meeting
we
minute.
anytime we meet, are we going to write it or we just wait
Yeah, yeah,
for
yeah, yeah,
do
yeah.
what?
Yeah. So your report that I'm expecting should be a report on all the week, like all the week. In fact, I wish you could type it out, but I know your typing speed and your skills is bad, so I know you can't type. But what you can do would be to get of a plain sheet, and every day you meet, every day, every particular day that you meet, every day that you meet. So every day, whatever day you meet, for each day that you meet, you would write the meeting start time and end time. Then the agenda, what you guys discuss, it includes everything discussed. So there must be a secretary. Everything discussed in the group, then your resolve in the group. For instance, you say, oh, we are committing this tax to this person. He should go and read about this and educate us the next time when we come. You have to put all of that in the group. Then the number of members that was present, the number that was absent.
Yes, sir.
Then that particular day, all the worked examples that you worked. All of them. Not, you don't leave anyone behind. All the worked examples you included in the, in your minute when you're submitting it. Please, we understand.
Yes, sir.
Great. So whatever day you meet, you need to get me at least these 5 things in your report for every day that you meet. So I think it will be good you use these plain sheets. It will be the best, form of reporting. So you can keep writing and writing and writing. Or you can get ruled sheets. You can get official sheets and all. You just split them apart and then you staple them together when you're done. And you submit it. Your handwriting should be something I can see. Now, if you're able to learn how to write minutes, when you go to the industry, you won't suffer. Because most of the times, an engineer that also knows how to write minutes will be put in many meetings so that you will go and write those minutes there. So whatever, when they're going for meetings, you are meeting of engineers, you're an engineer, but they will ask you to write the minutes for the meeting. And that will be an advantage for you in the industry. So that is why I want you to build that skill now. Is that right?
Yes, sir.
Okay, great. Thank you very much. Any further question before we move on? Now, one thing that I've observed is that you guys, the 555 timer, we didn't really go deep into it. Yesterday, one of my mechanical engineers, my students came to my office and he was like, say, I really want to do PLC. I want to go into PLC. And I was very happy for him. I really congratulated him that he has that goal. But the problem is that for PLCs, you need to know basic electronics. PLCs are built out of basic electronics. When you go to the industry, everything I'm teaching you is something that you are going to use in the industry. It's not something that I'm just picking from, some theoretical, play somewhere. It's just something that you will use every one of them. Every one of the things that I'm teaching you in the industry when you go there. So I really want you to take everything serious. And like I have told you, not because of the exams, but because when you go to the industry, you need them. You shouldn't say that, oh, this formula, I can't put it in my mind. It's always in the book, so I'll come back to it. No. When you go to the industry and you're designing things on the fly, people are not really going to wait for you to come and then consult your books or something. You would have to know it on the fly and then give us the information. And this book is not something that you can't learn. Even a QLI and Co, you learned them when you were in senior high school. In a book, K12 now information. So you guys should really up your game and then let's work hard to put all of this in mind. So I would stress on the 555 timer when you guys are doing your revision when you meet, because you'll be getting interesting questions from the 555 timer in your exams. Then the filters, the low pass and high pass filters, you also be getting interesting questions from it. With a capacitive filtering. We've already discussed all of these. Then impedances and co, we've discussed these already, and you'll be getting questions from them in your exams. So kindly take note of all of this. Is that right?
Yes, sir.
So today, let's proceed and then continue on chapter 4. So chapter 4, we are done with chapter 4.1 and 4.2. The next very important thing we need to consider is chapter 4.3, called The diode.
Okay.
The diodes. Diodes. Now, diodes are very, very, very important circuit elements that we use. Very, very, very important circuit elements that we use. Have you, okay, I know that you guys are mechanical engineers, but then you will have known about one-way valves, right? Have you heard of the one-way valves before? A one-way valve.
Yes,
No, sir.
please.
Okay, what's a one-way valve? Someone said yes. Please talk to us. What is a one-way valve? Yes, what's a one-way valve? Let's be very quick on this. Oh, so biology, you didn't do one-way valves in the human body?
No. No, sir.
Hey, teachers know me warm number and come from papa. Yes, and then please talk.
No, we didn't do anything like that.
Sir,
Listen, with the valve, it prevent the backflow of blood.
The
In
backflow
the
of the detractor agu teachers. Who teacher no one draw DBC and show say the heart valves or the valves in the body, they looks like this. No me.
Valve. Hey.
Once you have you don't remember drawing this.
the
You
guy,
don't remember this.
Yeah.
I'm sure.
Yeah.
Bana mu detrago mu teachers so sa next semester and me chere we abet before say me call class but my gym teachers ni na number. Eye pe na ma from say omu gu ani mu ase wa ha gushi o ma ho cha wan so. So this is a one-way valve,
Wow.
right? And the heart has a lot of these so that blood that is pumped under high pressure cannot fall back suddenly, because if all of that pressure is returning back suddenly, it can cause a grievous harm to the heart. So we have these one-way valves within the heart so that blood does not fall back suddenly. Now, in electronic systems too, we also have these one-way valves for current. But these one-way valves for current are called diodes. Diodes. If you look at it, but then diode, diodes. They are very, very important. Very, 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 very important. Very, very important. In fact, without them, I doubt that we can use any machine on earth. And so any machine you meet in the industry, you would find one of these guys there. We call it a diode. So you can take your hand out and be looking along because that's what I'm using. Right? We call these ones a diode. Now, what it means is that current, if I draw a diode and I say this is how it looks like, it means that current moves that way. It moves from the anode to the cathode. Now, the positive side is called the anode, and the negative side is called the cathode. Just like how you know, so that's the anode. And that side is marked positive, and this is the cathode. And that side is marked negative. Now, what it means is that if I connect a diode like this, then current can only flow in this direction. Current can never flow in the reverse. Is that right?
Yeah. Yeah.
Great. So diodes are one-way valves for current. So that current is always able to flow in the direction that we want it to flow. It won't be flowing in any direction we don't like. No, we don't like that. So we can get current to flow in one direction. Please, do we understand? And do we all agree?
Yes, sir.
Okay. Any question before I move on? No question.
Yes, sir.
Okay, great. Now, how do diodes behave? How do diodes behave? What are the behavior of diodes in circuit? So, number one, there are some characteristics of diodes you need to know so that you can use them. There are some characteristics of diodes that everybody who likes diode or who wants to use a diode must know so that you can use these diodes. Number one, a diode is said to be forward biased. I will not ask you in the exams what are the characteristics of a diode. Maybe exam na practical. It won't be what is, no. A diode is said to be forward biased if the diode conducts. So I would say, let me draw this circuit here for you. If I have my diode like this, and I say this side is positive and this side is negative, and I have my cell, my battery, is this diode forward biased? This drawing here, is it forward biased?
Mm,
Is it forward biased? Will it conduct? I mean, will this diode conduct?
yes,
Electrical. Will it conduct?
Okay.
yes, please.
Okay.
Someone said
Yes.
yes. Please, I'm Uncle Genevieve. He said yes. Why will it conduct?
Say it's not me. I haven't talked.
Hey. So who said yes?
This is no.
It's no.
Genevieve
Why no?
said yes. Randa, when did you come here and
The
tell me?
reverse bias.
Thanks,
It's not
Rahanda.
Randa.
Says she like doing his hair. I know his hair.
Ah,
Yes,
It's what
sir.
Genevieve who said it.
Rahanda, Kitty please. Why is it? Why will it conduct?
I get it on.
Rahanda is not here. Okay, yes. So someone said no. Why
Randa
won't
is
it
not
conduct?
here.
Yeah.
Please, this is a
What?
reverse bias.
This is reverse biased because it's not forward biased. So when you look at it, we said that is forward biased if we have properly connected it. Is that right? So we said that a diode is a polarized device, so it's having a positive and a negative part. If I connect the positive to a negative part, will it work? And if you look at this drawing here, this battery, that's the sign, right? The small one is the negative and the large one is the what? Positive. I hope you know that sign convention.
Yes, please.
Good. So if you look at it, we've connected negative to positive and positive to negative. Will it work?
Yes.
No,
No,
it won't
sir.
work. It won't. Is that right? Because it is reversed bias.
Bias.
Please, do we understand?
Yes, sir.
Good. So a diode is said to be forward biased if we connect it in a right polarity. So we have this positive one, positive, negative. Then, we would connect it to the diode like this. Then this diode is said to be forward biased. So it conducts. In this case, it is what? Reversed
Yes, bias.
bias. So these are the two states a diode can be in. Either it is forward bias or reverse bias.
Bias.
Please, do we understand?
Yes, sir.
Okay, great. Now, when a diode is forward biased, it has a certain property, and that property is very, very, very important.
Sir,
Yes,
please question.
yes, please.
Please, you said the positive side is the anode and then the negative side is the cathode.
Yes, please.
But then I thought the cathode, in the reverse bias, the anode is connected to the negative terminal, and then the cathode is connected to the positive terminal.
So that's what I've done here in this circuit. You see that this negative is connected to the positive here.
Okay,
Have you
sir.
seen it?
Yeah.
So this one is reverse biased. Okay,
Thank you.
that was a good question. Now, any other question before I move on?
No,
So,
yes.
Okay, now there are certain characteristics of a diode that we need to know. When a diode is forward biased, what it means is this. So it is not that the moment you connect a diode to a certain voltage, then it becomes forward biased. No, that's not how it works. How it works is this. Whenever you connect a diode to a voltage, so when I have a voltage supply here, then this is a diode. Then let's say we have a resistor and this goes to ground. What happens is this. Now imagine that this voltage supply here that we call VS, at times we call VCC, is a symbol for voltage supply. So when you see VS or VCC, it means voltage supply. Then this one goes to ground, which is represented by GND. So current moves this way to ground. Now look at what happens. Let's say that the voltage is starting from 0. The voltage is starting from 0. The supply voltage is starting from 0. It's building up small. So it starts from 0. Then it increases to 0.1 and increases to 0.2. So here is 0.2 volts. And then ground is always 0, right?
Yes, sir.
Ground is always 0 volts. So here is 0.2 volts and 0 volts. So you may be thinking that the moment is positive and then it starts from 0. It starts from 0.2. The moment the positive part is greater than the negative part and there is a positive voltage across it, the diode will start to conduct. No, it won't start to conduct. The diode has a certain behavior that it needs a certain minimum voltage before it starts to conduct. We call that a latch. It needs a minimum latch before it starts to conduct. So when the voltage starts from 0, it would be there. Then so you increase to 0.1. It doesn't meet the minimum. In fact, there are several types of diodes, and every diode is having its own latch. Now that latch is what we call knee voltage or forward drop voltage, VF. Knee voltage or forward drop voltage, right? So knee voltage or forward drop voltage. So VK is equal to VF. In fact, you will see these two things in the data sheet of diodes. That's why I'm telling you both of them. Now for a diode that is made up of silicon, and most diodes are made from silicon. So at first, when we started making diodes, we were using germanium because germanium was easy to use to make a diode. Very, very easy. But silicon was very difficult to fabricate a diode from because it required a lot of purity. In fact, right now, all our devices that we use, is made up of silicon, made from silicon. And you know, silicon is one of the most common elements on Earth.
Yes.
Silicon is found in stones and in all the sand around us. The sand is made of silica. So all the gravels and the sand around us is made of silicon. That means that silicon is the most abundant material, in fact, one of the most abundant elements we have around us. So if you want to make any material based on silicon, it's very simple. You just have to go and fetch gravels and you will just process it and get your chips. So all the chips, the ICs, the NVIDIA chips, the processors, all of them are made from the sand that is around us. But you may think that, okay, if we are making all of these from the sand around us, then it's very simple. We should, why isn't everyone doing it? That's where the problem comes. The sand around us is not silicon, it is silica, which is a combination of silicon and oxygen, some amount of oxygen in it. Now, what that means is that before you can really get silicon out of it, you have to extract that silicon from this silica. And that is where many countries in the world have not been able to break through. In fact, I've always been pitching that a country like Ghana should have at least a few people in the silicon making phase. Yes, Precious, you have your hands up.
Okay.
Carl Precious, do you want to say something? Okay, great. Maybe it's an accident. I've been saying that we, Ghana, as a country, should be looking at starting to train some of our people in the manufacture of chips and silicon chips. But unfortunately, I've not met any big man. All the people I'm talking to, they are not big men, so they don't understand what I'm saying. But I'm telling you because, you know, some of you in my class, you are big men already. You have access to these big men. Whenever you meet those big men, tell them that it is as part of our national security strategy. Someone said she can't see my screen. Please, can someone see my screen?
Yes, sir.
Okay, then kindly check your network. The network is very bad around this time, so you can disconnect and reconnect again. Maybe it will work. I'm so sorry for you for that. As a national national security strategy, we as a country should be able to have some of our youths building chips for us. Because imagine that, like I've always been telling you, the whites, imagine that one day they tell us that, look, they're not going to sell these chips to us again. What will we do? How will we be able to repair our devices? How will we be able to build the technologies we want to build? So whenever you get to meet them, please tell them that you are the young ones coming and you want them to start taking some of your those people that do national science and math quiz like this, they're very, very intelligent. And we can train them, they can take them outside and train them to go and develop chips and come back to the country. So when you meet these guys, please tell them this. Now, the reason why we have these different elements is that silicon is very good. In fact, like I was telling you about the purity level, the purity level we need is to get a silicon wafer, right? So we call that a silicon wafer that is chopped down. That is having a level of purity of 99.99959% silicon. And that is where many countries are not able to make these chips. That's why some very few countries are the ones doing it. In fact, in the whole world, Taiwan is manufacturing about 70% of all the chips we are using. So all the diodes, all the whatever, the diodes that we use, all of these are semiconductor materials made out of silicon. And you see that when we're talking about semiconductors, I told you that these are devices that you can selectively control their conductivity. And that's why we can make a diode. Because if we are making a diode, then we can select that if you are going this way, then the conductivity is very high. But if you want to go this way, then the conductivity should be low or no. Is that right? And that is why all these diodes are semiconductor materials, because we can selectively control how conductive they are in whatever direction or whatever moment we are looking at. For silicon diodes are very good. They are temperature stable, right? They don't behave erratically with temperature. At first, germanium didn't need that much purity. Germanium's purity wasn't very high, so it was very easy for you to get a germanium diode. But the problem is that germanium was very sensitive to temperature. The moment temperature changes small, then its behavior will start changing. For instance, the knee voltage. Now, the knee voltage depends on the material that you use to make your diode. If you're using a germanium diode or germanium material, then the knee voltage is 0.3 volts. If you're using a silicon material, then the knee voltage is 0.7 volts. But this germanium, if temperature increases by 10 degrees Celsius, then its knee voltage will drop by 0.1 volts. And that became a very, very bad problem, because imagine you design your circuit hoping that it is going to have a knee voltage of 0.3, and because temperature changed, it has dropped. You know, what that means is that your device can get bent if there are excessive voltages around, right? Because its temperature ratings it starts to drop, it starts to fall when temperature rises. Its voltage ratings fall. So if you had rated it for 5 volts, then because temperature has risen, its voltage rating has fallen. That means that 5 volts now becomes too high for it. So it needs a voltage of 4.8. Meanwhile, when you were designing the system, you provided only 5 volts. So the moment temperature rose beyond what it can tolerate, the device that was working well at 5 volts will now burn at 5 volts because temperature has risen. So germanium was that noisy, and we didn't really like germanium, right? So we had to research. In fact, I was not part, the white, the research that we Ghana, all we know is jealousy and envy and hatred for one another. But they are using their mind to work, not like us that we are using our minds to envy one another and pull one another down. I know that a new Ghana is rising. I hope that we are not going to be part of that. So they researched and built the silicon diode. Now, the silicon diode is the most common diode you are going to see around. And the knee voltage for the silicon diode is 0.7 volts. So what that means is that, let's take in our case here, this voltage scenario we are looking at. If the voltage is 0.2 volts, that means that the silicon diode, it will not turn on. Is that right? Because it needs a minimum of 0.7 before it turns on. So when it rises to 0.5, it's still off, because that voltage is not enough to turn it on. It's not enough to bias it. But the moment it rises to 0.7, then it starts turning on. But when it turns on, there will be no voltage at the output. So look at what happens here. If the voltage here at the source, or let me say the in to it. So this is V out. Now, V in, V out. So if there is a voltage here, sorry, the voltage at V in is 0 volts, then the voltage out will be what? 0. If the voltage at V in is 0.5, so let's say this is a silicon diode. So let me put silicon here. If it's 0.5 V, V out will still be what? 0. Is that right?
Yes.
Because 0.5 is not up to 0.7. Please, you understand? You can react by the thumbs up so that I see if you understand. You can just give me a reaction instead of unmuting and replying me. You can just give me a reaction. Thumbs up, something. So it shows me that you understand. Great. Thank you very much. So if the voltage rises to 0.7 volts, then what happens is that the diode will turn on, but all of that 0.7 volts will be latched here across it. So all of that 0.7 volts now, baby. So the diode cannot conduct That's 0.7 volt to the output. So at 0.7 volts, here will still be 0 volts because no voltage will come. Now it has turned on. So usually we look at it like this. We look at it like this. So let's say I have a bridge. Then this bridge that I need to cross is having a height of 0.7. So if I'm able to supply 0.7, I just cross it. But I can't continue again, Maka. Please, you understand? But if I'm able to supply it 1 volt, then what happens is that the 0.7 stays here, then the remaining 0.3 will come. So the output will be 0.3 volts. This is how a diode behave. Yes, so unless it's above 0.7 that it can cross. So the excess. So the diode it will latch a minimum of 0.7. Is that right? A diode will always latch a minimum of 0.7. Please, do we understand? Now, what that means is that let's say I connect a diode here like this. Let me just say that there is no resistor. I connect a diode here. Then this one goes to ground. If this one is 5 volts, this guy will latch 0.7 volts. So what will I get at the output? Yes.
4.3.
I'll get what?
4.3.
4.3.
4.3.
Yes.
So in your exams and your objective, you can be getting some of these questions. You know me. Yeah, you can get some of these questions there. Please, do we understand?
Yes, please.
So that is the behavior of a diode in the circuit. Now, a diode, somebody is asking in the chat that he learns a diode can still conduct current. Yes, a diode can still conduct current. That is why we have the IV curve. So let's discuss the IV curve. But before we talk about the IV curve, let's talk about certain properties of a diode. In fact, diodes are several types of diode. In your handout, you can, in page 98, you can see that a diode has, so the common diode, in fact, the diodes I'm ordering for you as part of your kit is the 1N4001, not the 4007, 4001. Now, when a diode is connected in reverse, there is a maximum voltage it can stand. So in this reverse bias connection here, if you connect it in reverse, there is a maximum voltage it can withstand. If that voltage here, this voltage here, exceeds the maximum reverse voltage, the diode will break down. It will spoil. It will get spoiled. Because diodes are semiconductor devices. And so we dope them to get a behavior that we want. If the doping that we did, it has a certain threshold it can withstand. If that reverse voltage exceeds that threshold, the diode will just break down. So we call that the breakdown voltage or the Zener region. So the breakdown voltage or the Zener region. I hope you can see it from your handout, right?
Yes, sir.
Good. Very, very good. Very, very good. So for the IN401, when it conducts in the forward direction, it can pass a maximum of 1 ampere current. So take note of that. You see, in all the classes and all the things that I'm teaching you, I tell you the current rating of all the devices. I tell you the current rating of the resistor, the maximum power rating, so that when you're designing your systems, they will not get spoiled. Now, the diode also have a current rating. Every diode has a current rating. For the 1N4001 diode, the maximum current that you can successfully pass through it is 1 amperes. Any current more than 1 amperes, people who say, "What you want? What we see a pampan." Not just a diode, no, I media. Is that right? So whenever you are using the one and whenever you are designing a circuit, you first of all have to go and look at the data sheet of the diode. We call something data sheet of a diode. You just go online and search. So there are several types of diode. You can first of all, when you design your circuit, you may need 2 amperes. Then you just go to Google, Gemini, or whatever, and you search what diodes can pass 2 amperes of current. Then it will give you some part names. You get those names. Then you go and look at the next thing to look at is the maximum reverse voltage. If you are connecting it to the mains, right, then the maximum reverse, you know that the maximum voltage of an AC current is 325 volt. Please, who is talking behind there? Somebody's giving me feedback. Kindly mute yourself. The maximum voltage of an AC is 325. That means that if you connect the 1N4001 diode to an AC, it will get bent because the maximum voltage is more than it can endure. So by the time you realize, you'll just be seeing smoke. It will just get bent. So you first of all look at the current you need. Then when you get the current you need, the next thing is to look at the maximum reverse voltage. Then you base on this to select your diode. Now, when you select your diode, the one other very, very important characteristics is the forward voltage or the knee voltage. You also have to look out for the forward voltage or the knee voltage. The reason why we need to look out for the forward voltage or the knee voltage is that if, let's say that you're designing, any system, right? You're designing a system. The system that you are designing will be working in, it'll be working in a large circuit, working with certain components, right? Now, if you don't meet the minimum knee voltage requirement, will the diode turn on?
No.
No, it won't turn on. So you need to consider the knee requirement and build your circuit in such a way that you can be able to pass the minimum voltage requirement that the diode need. Otherwise, the diode will not work. Diodes are like that. People don't know how diodes behave. They just think that once you connect a diode, so no, and so sir. So it depends on the material that was used to make the diode. So if you look in your handout page 98, you can see that I've shown certain diodes, special diodes like LED, light emitting diodes, diodes that can give light. Most of these diodes are made of different materials. So a diode that is made of the amber color, right? It looks yellowish. It looks like fire, That amber is made up of aluminium, indium, gallium, phosphate, right? It's a composite. In fact, when they were researching these LEDs, to discover that this material is what can make this color was years. It took years, in fact, years and years of research. So I always say that we, the modern day humans, we are taking a lot of things for granted because we think that, come on, this is nothing. This is nothing. Well, the white LED and the blue LED like this took about 8 years of research to discover that the material that can make a blue LED is where is it? I'm trying to. Wow, I really like the questions. Wow, Precious is asking. I really like the questions she's asking. Very, very, very good questions. Great. So, okay, great. So I have this here. All right, now, so if you look in your handouts, we are here. There is this table there that I showed for you to see. Please, can you see the table?
Yes, sir.
Good. It took years. So this small table that you see here took years, years and a lot of money to discover that we first of all discovered the orange, the green. So these ones were already discovered. We discovered these ones, the green, the orange, the red. They were very easy to discover. Then the yellow. Then the blue. The blue became a hell. The blue LED alone took 8 years to discover, and it was discovered by one man. In fact, there were several men that were researching on the chemical, what kind of element can make a blue LED. So they discovered the red. The red was easy to make. The yellow was very, very easy to make. The amber was also very easy to make. The green, yes. But the blue, making this one was very, very, very difficult. Now, I told you that the forward voltage depends on the material that is used to make that particular LED. Now, so all of these, so once we have a silicon, you see, none of these is made up of silicon. But if we have a silicon material, then its forward voltage is 0.7. But if we have a blue LED, which is made of gallium nitride, then its forward voltage is 5. That means that if you are going to use, please, someone is giving me feedback. Kindly mute yourself. That means that if you are going to use a 5 volt to turn on a blue LED, then you would really have a problem. In fact, these days, they've been able to make blue LEDs that are having a lower forward bias voltage. Some are having 3, some are having 2, but some are having 4. So we have some diodes that have a lower, some LEDs that have, some blue LEDs that have lower forward voltage, because research is still going on. People are still researching to get a lower forward voltages. Now that means that if you have a voltage that is, if you have a diode that is having a higher forward voltage, you need high voltage to be able to turn them on. So for instance, for a blue LED that is having a 5 volt forward, voltage, it means that you need a voltage that is greater than 5 to be able to turn it on. If your voltage is not greater than 5, you will not be able to really turn it on and let it bright. So, but I've told you that our mobile phones uses, 5 volts, a maximum of 5 volts. In fact, most of the ICs use 3.3 volts. So if you want to turn on a 5 volt LED, that means it is not going to be possible if you're using a mobile phone. Or if it's going to be possible, the circuit would have to be large. And so we really don't want these large, forward bias voltages. We want to get smaller diodes that are having smaller, forward biases. And so research is actively going on. The material scientists and the some of these chemical, electrical guys are really working on it to discover materials. So new materials are still being discovered. Is that right? Great. All right. Any question? Somebody has asked, what's the difference between a polarized and unpolarized diode? So diodes are always polarized. We don't have an unpolarized diode. When we say polarized means it's having a positive and negative, part. So when you say that a diode is unpolarized, what you're trying to tell me is that the diode is not having a positive or a negative side. So diodes are always polarized. That's why we call them diodes. Okay, great. Now, any question before I move on? So in your exams, I can ask you to draw the IV curve characteristics of a diode and explain it. And you should be able to do that.
Oh,
The IV, yes.
say.
The IV characteristics of a diode. In fact, you should be able to draw this and explain it. And that is the circuit. Now, if you have a diode, yes. Great, so we will come there. I like that question. Qual President is asking me what will happen when you connect the resistor parallel instead of series for LEDs. We will come there. We'll take some circuits on that very soon. But then, let me explain this IV characteristics or IV curve. So when you have a diode, then let's say that this side is a current side, and then Avia Sewa, are you on the line? Avia
Yes, sir.
Sewa could be. Oh, great.
Down here.
How are you?
Totally, I'm fine.
Great.
Oboku,
I hope you understand what we are learning.
Yes, sir.
Are you sure?
Yes, sir.
You know, when you're a student and you talk in class, that's when your lecturers will know you. If you don't talk, they won't know you. So if I call her, it's because she speaks in my class. She's active. She disturbs me in class, and I also disturb her back. Now take her. But you come to class, you don't talk. Japan is our name. You see. So please ask me questions so that I'll know you if you are not talking. Now, I've told
Okay.
you that. So here's the voltage side. Now I've told you that for a diode, it will not turn on unless the voltage is having a minimum of 0.7 or what we call the VK. So when all the voltage is below 8, it's 0. All the voltage is 0. But the moment you exceed that, and no current will flow. No current will flow when it's not turned on. The current that will flow is microamperes, very small. It can't do any work. So the moment you exceed that 0.7 now, then connection will start. Then current can flow exponentially, right? Current will flow exponentially. So it's not a straight line. So here is like this now, and then it starts like this until it reaches the maximum that it can take. You see, I told you that every diode is having a maximum. So when it reaches the maximum, it can't increase again. Then it stays there. Now, in the reverse side, what happens is this. Okay, hold on for me. Oh, great. So in the reverse side, this is what happens. So you should be able to draw and explain this curve for me. In the reverse side, I told you that a diode can, when it stays in reverse, it's not conducting. So when a diode is in reverse, it's not conducting. It won't conduct anything. It won't conduct anything. But the moment you put a voltage greater than its reverse, maximum reverse, or the breakdown voltage, you see, I told you that any diode is having a breakdown voltage. So when it exceeds that breakdown, then the diode will suddenly conduct. It will act like a conductor. So this diode will always conduct. Until that diode not say, not so I be a conductor. There's no more a diode. It will conduct whatever current you connect to, it will conduct. So we call that the breakdown voltage or the Zener. This behavior was discovered by, so we named it after the person Zener. So we call that the Zener region. In fact, we have special diodes called Zener diodes. That their behavior is to operate. They work there. They work in the Zener, region. They work as reversed. Okay, so this one here is called the VBR. In fact, some people call it VBV. Please, do you understand? Where VBR is equal to breakdown voltage. So breakdown voltage. So BR or BV. So BR is still breakdown. BV is still breakdown voltage, right? So these terms are used interchangeably. When you meet them, you shouldn't be confused. So you should be able to draw this and explain how it works. Yes, Abeka.
Sir, as you started, you said
Yes.
the moment the current flowing through or the voltage reaches 0.7,
Yes.
then the diode will start to work. And I'm
Yes.
asking, is 0.7 a standard number or figure for all diodes to start working, or because first as you started, you said there are two main different types of materials diodes are made for. And
Yes.
the germanium ones start at 0.7 and the silicon starts at 0.3. So is the 0.7 a standard figure for all diodes or what?
Okay, great. Can anybody answer him for me? I want to see if you guys were paying attention. Yes, can anyone answer him for me? Yes, Rosina. Great.
Okay, so when you were talking about the diodes and their
Yes.
power, this one,
Yes.
you said that for
Mm-hmm.
silicon diodes, their
Mm-hmm.
free voltage or their forward voltage is 0.7 and germanium one is 0.3. But for
Great.
germanium, it's sensitive to temperature. So mostly
Great.
they use the silicon diodes. So
Okay.
for all of them, they use silicon, and then
Great.
the forward voltage is supposed to be 0.7.
Great. Thank you very much, Rosina. God bless you for your submission. Yes, Asamoah Eclipse, my name. Let's go. Asamoah, please talk. Unmute and talk. Asamoah, we are not hearing you. If you're using a Bluetooth speaker, maybe it's not working properly. You can disconnect it and speak live into the phone. Okay, so Richard, talk. Asamoah is not, his feed is not coming through. So Richard, let's go. Then Dankwa will follow.
Is it? So which
Yes.
means any
Mhm.
diode that's made of silicon has a forward voltage of 0.7.
Exactly. That's
Okay.
the point I'm trying to carry across. Any diode that is made of silicon has a forward voltage of 0.7, regardless of how large the diode is, regardless of its maximum breakdown voltage, regardless of its current. It needs a minimum of 0.7 volts to turn on. And so it will latch a minimum of 0.7. If you give it 5, it will take 0.7. Then the excess is what he will pass on to the next devices.
Thank you, sir.
Great. You're welcome. Yes, Hassan. Hassan, please unmute yourself and speak. I don't know why I'm not hearing Asamoah. I can see he's speaking, but I'm not hearing him. Asamoah, phone nitibomo. Hassan, please talk. Asamoah is seriously talking. No, I can see he's seriously talking. His microphone is showing active, but does anybody hear Asamoah?
No, sir.
No, sir.
Asamoah, your microphone is why your microphone bunny? It's all compared because you be part of microphone. Or you can use your laptop. Or you can type it in the text box for us and then we would look at it for. But this class, you are really regal people. Oh. We have Osei Tutu is here, then Afia Sewaku. Like, I am from one class out. As I'm by granny. Nature man,
Yes,
yeah.
sir.
In phone kwa.
Empe you won't go. Where you go Kasama or no check a grabby pair. You're throwing him few.
Wake up one say.
Me say, what a cross no crown now, picture. Okay, great. Someone please type your question in the chat. Say, yeah. All right. So please, did I answer your question? I'm even forgetting who asked it. Did I answer your question? So I said that the forward voltage of a diode depends on the material that is used to make it. If it is silicon, is 0.7. If it is germanium, is 0.3. Then I told you that all the LEDs, the light emitting diodes that we have around us. In fact, LEDs are around us. In fact, your phones, the laptop screen, the phone that you are using to watch me this morning, the screen is made up of diodes. Diodes are so important. Without diodes, this world, I don't know how it will function. your mobile phones, the screen are made up of small diodes. Small diodes in it. That is why you see we call them OLED, right? Organic light emitting diodes. That's the meaning of the OLED screens. So when you see OLED, my phone is OLED, my phone is LCD. That one is a different technology. LCD. So most of the phones, some of the older phones are LCD. And then most of the recent modern phones, the Samsungs and the iPhones, they are all OLED, organic light emitting diodes. So diodes are around us everywhere. Our mobile phones, our screens, our laptops, our chargers, diodes are everywhere. And they are so important. Without diodes, I don't know how we can use our modern equipment. And this is how they behave, right? Now, when we were searching for the LEDs, I told you that all of these LEDs have their forward voltage. I think maybe you were not on the call, so I showed this screen clearly. And I said the blue LED is having a forward diode, a forward voltage of 5.0. In fact, we are bringing it down. Some of them has as low as 3, right? And then we have the white LED that has a forward diode of 4.1 volt. And observe that the white and the blue LED are all made from the gallium nitride. Gallium arsenic phosphorate, right, was one element that we discovered early and was easy to make, but gallium nitride was very difficult to make. Now, how do we use these LEDs to make our mobile phone screen? Have you observed that we said that there are 3 primary colors? And out of these primary colors, we can form all other colors in the world. We told you in senior high school that the 3 primary colors were red, green, and blue. And from red, green, and blue lights, you can form all other lights in the whole world. If you combine red and green, you get the cyan color. If you combine red and, blue and green will give you cyan. If you want to get yellow, yellow is a combination of red and green, right? Yes. So what we did was that if we want to, so in your screen, in your mobile phone screen, so we call it a pixel, picture element. So when you are using an iPhone, we can tell you that your iPhone is 2048 per 790 something pixels. What it means is that those are the number of LEDs in your phone screen. So that's the number of LEDs that we are telling. We call it picture element. That's the number of LEDs in your phone screen. So each of these LEDs at that place is made up of 3 LEDs. We have a red, green, and blue LED. Now, with technology, we can determine the concentration of red or how much red we should show at any point in time. So whatever picture you are seeing on your screen, the phone is actually calculating for each of those little pixels. What should be the concentration of red I should show here? What should be the concentration of green? What should be the concentration of blue? That is why at times your phone can freeze when you're playing high resolution games because it's randomly calculating this and it's performing all of this calculation 1 billion times in a second. That's why at times your phone can freeze, right? Because it's changing, it's updating all of these LEDs to show you the color that you want to see. And that is the work of electronic engineers, and that's what they do. You mechanical guys are more of the material side. You are to help us discover the materials that will bring these typical forward voltages down. And if you take it serious, you can really make a very good living out of it. Is that right? Okay, so as someone has asked this question, he says, my question is, just as there is a knee voltage for the diode to work in a forward bias, can the diode be considered on when the same or maximum voltage above the knee voltage passes through it when it's reverse bias? That is a very brilliant question. That shows me that you really understand my class. Whenever I teach and my students don't ask me questions, I feel very embarrassed. And I am a yes. Now let's come to this graph. This is where your question is answered. So I said that if we have a diode, it's having 2 behaviors. In the forward bias mode is when you've properly biased it. You've connected positive to positive and negative to negative. In that mode, it will not start conducting unless the minimum voltage, the minimum forward or knee voltage, the minimum forward or knee voltage has been reached or exceeded. Then it will start conducting. But in the reverse bias mode, when you connect the diode in reverse bias, what happens is that in reverse bias mode, the diode will not conduct. It shouldn't conduct. It shouldn't conduct at all. So when you reach a minimum of 0.7 in the reverse bias mode, will it connect? Will it conduct?
No, sir.
No, it won't conduct because in reverse bias mode, it is not supposed to conduct. But when you start increasing the voltage beyond 0.7 and you reach or exceed what we call as the breakdown voltage, then the diode will just break down. It will crash. Within it, it will destroy. Then it will start conducting. Meanwhile, in the bias, in the reverse mode, it shouldn't conduct. But whenever you increase the voltage and it exceeds that maximum reverse bias voltage, it will suddenly conduct, but it must not conduct. That time you've destroyed the diode, it won't work again. It doesn't behave like a diode again. It now becomes a conductor because the maximum reverse bias voltage has been exceeded. Please, do we understand? Then it behaves like a conductor. All right, so Osei Tutu, hey, people didn't grana me machine. Osei Tutu me bajo kasawai. Let me find the student name for Osei Tutu. You have to call you Nana. See class I'm a Nana. Bajo, it didn't. Yes, so please unmute yourself and ask your question. You raised your hands first before all of them. Yeah, unmute yourself and ask.
Yeah.
Jose Tutu, oh, you are not able to speak. Please unmute yourself. If you are talking, unmute yourself. Okay, Richard, I think you have the mic, so let's talk. Let's go before Jose Tutu comes. Yes,
Okay, sir.
Richard.
Which means there's another region where the diode breaks, or
Yes, so the Zener, that's why we call it a breakdown. So the Zener region, in the Zener region, the diode breaks down. In fact, I'll go into details when we get to the Zener diodes.
okay,
But
sir.
in the Zener region, the diode has broken down and it can't really function. Kindly put your hands down if I answer your question. Emmanuel.
Sir, so
Emmanuel, yes.
meaning a diode hardly destroys when it's connected in forward bias.
Exactly.
Okay.
The diode, if you connect it in forward bias, it hardly destroys. But then it's also having a voltage rating. It's also having a voltage rating. So you make sure that you do not exceed its voltage rating. But all that we concern ourselves with is that so when I say, so look at something here. The voltage at the anode. So with all that I've said, I can summarize it in this simple expression that the voltage at the anode must be greater than the voltage of the cathode by 0.7 if we are using a silicon diode. In fact, we use silicon diodes so much. So whenever we talk about diodes, we always approximate it for 0.7. We don't waste time to, because silicon diode is what we use most of the time. So a diode will conduct if only the anode is greater than the cathode by 0.7. The moment is greater than the cathode by 0.7, it conducts. Yes. Emmanuel Asamoah has asked another question, very, very important question, and I really like it. He says, then why do we have to consider connecting a diode in reverse in the first place? For two reasons, two very, very important reasons. And I'll get into it in a few minutes. I don't want us to drink the soup before we get to the food. Otherwise, it will not be fun. You will forget. I want you to understand everything. So it will be easy for you to remember it. So we'll get there. But that's a very good question. Any other question before I move on? Okay, great. So now we are going to consider applications of diode in mechanical engineering. The first application of a diode is for light, for lighting, to produce light. To produce light. Please, if I have answered your question, kindly put your hands down so that I will not be distracted. Okay, great. Now, so we are going to talk about the LEDs, light emitting diodes. Light emitting diodes. What are light emitting diodes? They are like their name says, they emit light. Yes, is somebody asking a question?
Yes, sir.
Okay, then. Yes.
So I was asking that if the barrier potential of silicon diode
Yes.
is about 0.7 volts,
Uh-huh.
why does a tiny current still flows before the applied voltage reaches 0.7 volts?
Yeah. So these devices are not perfect. That's the thing. These devices are not perfect, but we consider them to have a zero flow because those currents is usually microamperes. You know, microamperes is so small. Microamperes is too small. Yeah.
Yeah, but also during the forward bias,
Yes.
does the external voltage actually eliminate the barrier potential, or does it only reduce it?
It reduces it. It's not fully eliminated. It reduces
They say
it.
why do you still treat the diode as having a 0.7
So
volt?
that's the forward bias thing that you're talking about. That's the depletion region. That 0.7 is to maintain the thin depletion region for you to have pass your excess current.
Okay, sir. Okay,
Uh-huh.
thank you.
Yes. So I don't know being for that depletion region. In fact, that's what the 0.7 is doing. It maintains that depletion region. To maintain that, it uses that 0.7 to maintain that depletion region. That's why you cannot have all the input voltage going to the output. Because you really need to maintain that depletion region for it to function. But when you connect a diode in the reverse, and because in the reverse it enters, the depletion region becomes large. When the voltage exceeds the holding capacity of the depletion region, then it breaks down. Then so there is no depletion region again. The thing just not free. It starts behaving like a conductor. So we really don't want to operate a diode in that area. So you always want to make sure that whatever application you're doing, the diode is his strength is not exceeded. Please, do we understand?
Yes, sir.
Hello.
Yes, sir.
Okay, great. At this rate, I think at 7 o'clock we'll still not be done with. You guys have a lot of questions, huh? But that's good. Shows me you understand what I'm teaching. So this is how the LEDs look like. In your handout, it looks black and white, but this is the initial color. This is how it looks like. So we have the LED, then we will put an opposite lens on it, then a LED chip. All right. Now, what I'm concerned about is this. Take note of this. The longest side, the longest leg is the anode, then the shortest is the cathode. So take note of that. If you connect it wrong, it will not work the way you want it to work. Okay. Now, how do we use it? There are certain elements of these, so we call these ones signal LEDs, signal LEDs, signal LEDs. Now, then we have proper one in our light bulbs, the one in our bulbs, the one you're using in your room right now. Those ones are light emitting diodes. They are just for light. But we have the signal ones, the ones in our laptops, in our chargers, our mobile phones, those devices. For signal LEDs, the maximum current, and you know that the brightness of the LED depends on how much current is flowing. Is that right? But the maximum current it takes is 20 milliamperes. Any current more than 20 milliamperes, the diode will be bent. See, you see, I told you that every diode is having its current rating. So any current more than 20 milliamperes, the diode would bend. It will just bend. Any current below this, it will not be its full brightness. Number one. So take note of that. That you're all the time making sure that it's not exceeding 20 amperes. In fact, the threshold is actually 25, but let's take it 20 to be on the safer side. Don't let current exceed 20 milliamperes. Now, look at something here. That means that let's say I'm connecting my diode. I have this circuit, VSS, VS or VCC here. Then I have my circuit here. If I connect my diode like this, so this is the symbol for LEDs with the light. Then I connect it straight. What happens is that if there is no resistor on this line, this current threshold will be exceeded, isn't it? Because there's no resistance. So the resistance of the line, which is very small, the resistance of these conductors are very small. So even if it's 5 volts here, the current that will flow here, I, will be equivalent to 5 volts over the small, because the lines are having very small resistance. So let's say the line is having a resistance of 2 ohms. Then the current that will flow through it will be 2.5 amperes. So what happens to the LED? You see that it will bright. It will bright power for some short time, then that's all. It just bends. It won't work again. In fact, when your kids come, you can try it. You can just connect it to the 5 volt LED. You see, it will be on sound for some short time, then it gets bent. It won't work again. So because of that, for us to use an LED, we have to use a current limiter. Another name for current limiter is called a resistor. So you use a current limiter, then you put the guy name. So the guy name for resistor is current limiter. That's the guy name. All human beings have a guy name. So these ones today have a guy name. Then this. Now, how do we select the size of this protector? So how do we select it? You've done Kirchhoff's and circuit theorem, so you should be able to do this. Now, this is how we select it. We said that when the diode conducts, if it is, whatever it is, it's having a certain knee voltage or forward voltage here. Now, if these guys are connected in series, that means that, so let me just draw the Kirchhoffs. Let me just draw it this way. So here's plus, here's minus. Then this one. So we have a resistor here. Then we have a diode here. Like this. Now look at what we have here. This is V, VS, VR. And here is what? Positive and minus. And this is VF. Let's write the Kirchhoffs. The Kirchhoffs voltage, the KVL. What will be the KVL? Yes. Yes, what will be the KVL for this equation? Let's start from VS. What will it be? Yes.
Minus VS.
Minus VS.
Plus
minus
VR.
VS.
Plus
Yes.
Plus
VR.
VR.
Plus VR.
VR.
Plus VF.
Plus
Plus
VF.
VF
Plus
is equal to.
Zero.
Equal to 0.
Okay. Please, we understand.
Yeah.
Yes, sir.
So let's make VR the subject. So VR is going to, because we want to find the resistor, the
VR
value of
equals
R. Right.
VR equals
So we are
VS
going to
minus
get
VF
VS minus
Yes.
VF.
Minus VR.
minus VF.
Great. Now we know that I times R is equal to VR, right?
Yes, sir.
Yes.
Somebody is giving me feedback. And this is equal to VS minus VF. So if you want to find R will be equal to Vs minus Vf over I. Now, this equation is something you really need to know. It's so important. So when you go to the industry and a certain signal LED has spoiled and they want you to replace it, this is the equation you use to replace that signal LED. How do we use this equation? Let's take an example from the book. Example 4.4. It says that we have a green LED and we are using 9 volts to power it. So what should be the resistance? So we have the Vs is 9 volts. Then we have a green LED. The green LED for the VF is what? 2.1 volt. Then we said that the current in a LED should not be more than what? 20 mA. Let's say we want it to be very bright. So we are going to use 20 mA. You can also use 15 mA. The book calculation uses 15 mA. But I will use 20 because I want it to be very bright. So what resistance should we place on the line so that the LED will be as bright as it can be? Meanwhile, protecting it so it won't get bent. So we have to calculate the value of R. And here is Vs. So R is going to be equal to Vs 9. So let's take the formula first. Vs
9 minus 2.1
minus V over I. So
Vs
9
over I.
minus 2.1 over 0.02. And what do we get?
If yeah,
Yes, if you are good, I was coming to call her. If Nana Afia Sewa, with the SSN, I'm afraid, Nana Afia Sewa, I didn't really son of it.
My calculator.
About him and Bajo Casamano.
So you get
Not with my calculator.
That is 345
345
ohm.
ohms. Are you sure? Okay, yes, 345 ohms. Do we have a resistor with this value in the E12? Hello?
I.
Are we going to get so that E12 values? You have to memorize them all because when I'm no control 345, mommy, I'm waiting. So 345 is there, but the answer is no because you don't get a resistor with that value. So you have to use the E12 values there for me. So as a E12 values no good. Our chapter 0.
Yes.
Go and revise there.
Yeah.
So we don't have this value there. So we are going to use 300 and what? 30
80.
degrees in the E12 values. Or you can say that you're going to use 330 plus a 15 ohms in series. You connect them in series and then it works. Now, when we choose 330, we need to come and recalculate and see if the current will not be more than the I. So you come and recalculate I, and I will be 9 minus 2.1 over 300 and what? 30. Which will give us what? Yes. Yes, what do we have?
0.0.
0.003.
Give it to me in milli.
Said 3 milliampere.
No, it's not 3 milliamperes.
20 milliamps.
So if you want to get the milli, when you press the SD, press the ENG key. Right? And you see when you press the ENG key, what do you get?
20 milliamperes.
20.9 milli
20.90.
9 milliamperes. Please, you understand?
Yeah.
So is this current good? Is this resistor good? Should we select it or no?
You should.
Should we select this resistor or we should select a lower one, a higher one? It means that a current of 20.9 mA is what will pass through it.
Into
Right,
that,
so
to damage it.
it will damage it.
Yeah.
That means it will damage it in a short time.
Yes.
If you use this
Yes.
resistor, it will damage it in a short time because it exceeds the 20 mA. So you can choose a higher one in the series. Then you use it to recalculate it. So that is how we design circuits. Please, do we understand?
Yes, sir.
Great.
So meaning the
Mhm.
0.9.9 above it is not negligible at all when it comes to
Hey,
this
it's not
stuff.
negligible. Oh. When it comes to current, Charlie, 0. If a device is rated for 20 mA and you do 20.1, it may shake.
Ish.
Current rating is very, very
Yeah,
serious.
what about
So what
20.001?
it would harm it, but it would take a long time before it harms it. That's the thing. So what it means is that the lifespan of the device will be reduced because you've exceeded the design rating. So all the time you want to stay within safe margins. You don't want to go close to that 20. That is why in the book I actually used 15 mA for the calculation. That way it stays long. You see, have you observed that the Chinese devices and check now say
Yes, sir.
these are some of the reasons why they don't consider these in their calculation. I told you the last time that there was one device I was using, my grandfather's radio. It was still working, Japanese. It was still working. Then I was just curious and I made them two tools already home. And I saw that they over-engineered it. The resistances, the power rating of the resistances, they used more than what was needed. So if this thing is working, then environmental influences come upon it. It still works reliably. But the Chinese, because they want to cut down cost, if the thing is a quarter watt rating, let's say that he did it and it was let's say the power rate when you calculate for the resistor, it was 0.25 or 0.24. China need no for quarter watt rating. A quarter watt rating can take 0.25. Yes, because it will make the device cheap. But US need no or calculate here power rating here 0.24 watt no. Though quarter watt a bit me. But when you say 0.24 is within the safety margin, so this device will spoil quickly. So he would choose a 0.5 watt rating. That will make it expensive, but when you buy it, you use it for long. But the China man, no, he's cutting down cost. So he'll give you that 0.25. Until the thing is working, all right, but the lifespan of the resistors is very, very short. And that thing is it's harming us because most of our waste that we are throwing away, which is causing this flooding, is contributing to it because you just buy a bulb and then you don't use it for up to a year. I bought some Chinese bulb. I used it for like 3 months per share. When I'm a year, imagine it's a China bulb pan, they mean to be. I bought one Indian bulb. Yes, I bought one Indian bulb, the light emitting bulb. I used it for like 7 years, 7 solid years. And so na bulb nation, me two free fear na me turn home echo different house. And na me two bulb na de call it. Cause now me per bulb na sempa. Ti me two no be beka sen kaminja bulb no debi. Me two me bulb no sign the call new house.
It's a wood to
And na me
our
the
people
shape.
count.
New house no me you soon for 4 years. Additionally, asana bulb nation. Bulb nation and my time they have to me them. I've immortalized the bulb because the bulb was well built. And that is why those bulbs are expensive. You go and buy the Chinese one, it's cheap because the
It
weight, the ratings of all
was
the
worth it.
equipment, yes, they are lower versions. So whenever you are designing a circuit, whenever you are designing any system, basic electronic system, you should look at the safety margin and always make sure that you are doing at least twice that safety margin. Otherwise, at the end, please, we understand.
Yes, sir.
Now you should be able to calculate the rest. So I'm not going to go on that. Then we have the application of the LED. We have the 7-segment display. So the 7-segment display is an LED that is made up of 7, displays. Let me share the image and then we talk about it quickly. Then we look at the last application for LED for diodes and we are done. If I want to go into details, we won't finish. Great. So these are the 7-segment displays that you have seen in your handout. So these 7-segment displays, we use them to write numbers. You see, if we have a 7-segment, the reason why I call them 7, you can count the LEDs. 1, 2, let's count the LEDs. You see, when you count them, they are 7. So 1, 2, 3, 4, 5, 6, 7. So if you want to write the number 1, that means you turn LED B and C on, then you turn A, F, E, D, G off. If you want to write the number 2, which LEDs will you turn on? Yes. If I want to write the number 2, which LEDs will I turn on? Yes.
A,
FE.
then ED.
FE.
So
AB,
FE goes
CED.
off. Is that right?
Yes,
Yeah.
sir.
Yes.
Yes.
And
Yes.
C.
So this one I can ask you in your objective. In a
Yes, sir.
7-segment display, if I want to write the letter F, or so the letter F, you can even use it to write the letter F. Which
Yes.
segments go off?
BCD.
BCD.
Good.
BCD.
And you should be able to tell me where I can A say no then on your frame. Okay, great. I said, what can I be samaji? As a samaji, we pusume. I said, Batakalina Meteran. Okay, great. Now, so that is a 7-segment display. And you will see it in most of the components around you. You will see them almost everywhere. Is that right? Now, let's look at the next application, and that's a rectifier circuit. So the rectifier circuit, in fact, we should have practiced it, but I was afraid that light bet will be in a mijay. I didn't want.
Light and should be
Yes, sir.
Yeah.
I didn't want to get
That light
shocked.
better.
Yeah, because if somebody go and hurt themselves, I'm the one to hold me responsible. So I was like,
Oh.
nah,
Yes, sir.
yeah, let me. This
Yes,
is
sir.
risky. You don't need to hurt yourself to learn. It's not necessary. You can just avoid it. Besides, look, all these adapters around us, they operate on that principle already. So you can just go and buy an adapter and use. Now, call baby. What I need from you is to know how to use a diode and no. And then you can just, hey, OBC, we are lightless. Masa, now you're lightless. Some people are lightable. But funny, you know.
Genevieve.
Yeah, Genevieve. But funny.
Sir, Richard is lying. It's him.
Okay, so Qual Precious says, can I go over it again? Qual, which part should I go over again? The 7-segment display or what? Show me a thumbs up. If it's a 7-segment display, just give me a thumbs up. Or you can write it in the comments for me. So, okay, 7-segment display. Let's go over a 7-segment display. So the 7-segment display, you've seen it around. You see, when you go to the filling station, you see that that display that is showing you how much fuel we've dispensed for you already.
Okay.
Yes,
Those
sir.
So
numbers
that's
there.
7-segment display.
That's a 7-segment
Okay.
display.
Yes,
Or
sir.
your
And
disco watch.
it refers to when they are doing changing in football.
Exactly.
The one
That's a
that they
7-segment
raise up.
display.
And
Exactly.
the guitar watch.
And digital watches, those are all the 7-segment
I have
displays.
some.
Yes, your FM radios, those are all. You see the FM radios, they write the numbers there. All of them are 7-segment displays. Exactly.
Okay.
You guys are brilliant. I like that. So yes, 7-segment displays. And we call them 7-segment because they use 7 LEDs, 7 LEDs to write the numbers. So if you want to write, for instance, the number 5 or the number 3, you will turn on the parts that I have shaded. You turn on LED A, LED B, LED C, LED D. Then you can write the number 3. Then you turn off the parts that I didn't shade. You turn off F and E. So there is a whole aspect of electronics dedicated to it. I'm teaching your seniors. We call it the digital electronics, digital logic design. I'm teaching electrical engineers level 300. There is a whole aspect of electronics dedicated to that 7-segment. It's very complex, but if you want to learn it, you need to come and pay classes fee for me to teach you during the vacation.
I'm
Pay classes fee. Oh, small, like 2,000, 2K pay.
pay.
We
Hey,
can talk
For 1
about it if
year.
you're interested.
wait, I'll pay for you, okay?
If you're
2K pay.
interested, I can organize one for mechanical engineers based on an application to mechanical engineering, and then you will learn it. Those of you that will be going into PLC and industrial control, it will really help you.
We will talk later.
Somebody says, I will pay when it reaches 10,000. Hey, asikafo or class hapa. Also, me say class hana asikafo nkwana mashi o moha. On to handout ana musu. Me we crank handout in me and 5K.
Oh, Sanka, you
Okay,
back
good.
it.
Okay, great.
Yeah, that one.
Now let's discuss. So you see, Eclipse asked me a certain question that why then do we need a diode in a reverse mode? Why is it important? Now, this is why it's important. We use it for something we call rectification. You see, I've told you that there are 2 kinds of electricity, the AC and the DC.
Yes, sir.
AC and DC. Now, AC, I have a call. Kindly hold on for me. Let me.
All
Jennifer Oprio. Hey.
right. Keep quiet.
Jen.
Class
Class
Moya.
class Zoom
Say,
kasa.
say,
That's so be
now I'm hiding, so keep quiet.
Okay, great. So we have DC and AC. Now, the DC is what we use in our devices. I've told you that all the mobile phones, the laptops, the whatever, they all use DC. But then AC is what we bring to your house. Right now, the AC, I've told you, you already know how the AC looks like. The AC looks like this. It's changing. And then DC looks like this. Now, when you are converting AC to DC, we call that rectification. Rectification. Then when you are converting from DC to AC, we call that what? Yes?
Amplification.
Inversion. Thank you for your submission. Yes, inversion. Inversion. So the opposite of DC to AC is called inversion. This conversion or in rectification, we use diodes. Diode is largely used for rectification because you see, we told you that. Now, when we say an AC, what it means is that it goes forward, then it comes back. It goes forward. So when you look at it, the first part is positive. The second part is negative. So the first part, if this is it, This part is forward, then it reverses. It's forward, then it reverses. Now, so if you think about it, if we want to force the current to always move forward, that means we need what? A diode, because a diode is something that would force the current to move in one direction only. It won't let it go in the reverse direction. So we use diodes to rectify AC. So in all of your power supplies, there are diodes there. Or every power supply, your laptop charger, whatever, your mobile phone charger, everything, there are diodes there. And they are the ones converting from AC to DC for you. Now, the reason why I'm teaching this is this. You may make your own device and you may say that I want to produce my own power for it, because if you go to the market, the adapters there are in limited ratings. You have 5 volts, 12 volts, 24, 48. Maybe the device that you are making, will need 36 volts. You will not get a 36 volts. If a 48 volts adapters, it's very difficult to get. So when you want to get your own special adapter, then you need to be able to know how to build a rectifier circuit for it. That is what I'm teaching. But then there is a whole course dedicated to making electronic power supplies, which we call power electronics. And that one is so advanced. It's, in fact, in UNE, they learn it in 2 semesters just to be able to make power supplies. They learn it in 2 semesters. And so I will not really advise you to want to do your own power supply. It's complex. But let's say you've built some small device that can just work with a smaller, lower version, then by all means you can do it. So how do we design rectifier circuits? There are 2 types of rectifier circuits. We have the half wave and the full wave. Look at something here. So you see that over here, the voltage is positive. And over here, the voltage is negative. So look at what happens. Let's connect a diode this way. Let's connect a diode this way. Yes, let's connect a diode this way and see what happens. When we connect a diode this way, it's taking time to load. So when we connect a diode, you see somebody saying, if say you knew you made it colored, you printed it colored for us, then you pay 200 cedis. So when we connect a diode this way, look at what happens. Voltage comes and is positive. All of this cycle is positive. So in that cycle, voltage is the diode is forward biased. Is that right? So it will conduct. It will conduct in that cycle. Then in the next cycle, when voltage is negative here, we use a different color for it. We use this lime color. In the next cycle, when voltage is negative, what happens to the diode? The diode is what? Reverse biased. So will it conduct?
No.
No. So it won't conduct. So it will be flat for you here. So in that way, the voltage we have is having an output, a fixed output. Please, do we understand?
Yes, sir.
Great. Now, that is where the reverse voltage comes in. That is where the voltage rating of the reverse comes in. Now, we know that this maximum side is negative 325. So that means that your diode must be able to withstand a maximum reverse voltage of negative 325. Is that right?
Yes.
sir.
Great. So that is where eclipse, that is where your question comes. That's why it's important. That's where it becomes important. So whenever you are building a rectifier circuit, please, the soft copy you will never get unless you crack it or you crack my laptop and then you hack into my laptop and then get it. But you never get it. I wish you the best of luck in that. So because if I give you the soft version, I don't know, it's not good. It's my intellectual property, right? And But you can buy it later on after school when you get big money. That one I can sell it for you for like $200, $500, you know. So yeah, after school when you get money, you can always come and buy the soft copy. Yes. Now, so in reverse, it doesn't conduct. So there's small leakage current, and those small leakage currents of microamperes, look, the resistance will let it die out. So it won't travel anywhere in the circuit. It will just flow through it and that's all. It doesn't travel anyway. So that one is not a problem. Please,
Yeah.
we understand.
So you were saying that
Mhm.
when you are building a rectifier circuit, you didn't
Yes.
continue.
So when you are building a rectifier circuit, excellent. When you are building a rectifier circuit and it's going to be a half wave, you need to select the diode so that the diode can withstand a maximum reverse, or it can have a VBR greater than, should be greater, not greater than or equal to, it should be greater than 325 volts. Because if the maximum breakdown reverse is lesser than this, the diode will not function. It will spoil. It will not be able to really rectify. Please, we understand.
No, sir.
So you see, I said that whenever the maximum in reverse mode, so when the diode is reverse, if the reverse voltage, the voltage that is connected to, is greater than the maximum is greater than the breakdown voltage of the diode, it will break down and will get spoiled. Now, we know that in our AC, I've told you this already, in our AC wave, the maximum voltage goes anywhere from positive 325 to negative 325. So that means that when the diode is reverse bias, a voltage of 325 is connected to it in reverse. Now that means that if your diode cannot handle a maximum of 325, when 325 occurs across it, it will break down. So for instance, when you have the 1N4001 who has a maximum reverse of 50 volts, if you're using it to build a rectifier circuit, what that means is that when that 325 volts appears across it, meanwhile, this diode can take only a maximum of 50. So since 325 is greater than that 50, the diode will break down suddenly. Then when it breaks down, you will not be able to get the rectification that you were looking for. So when you are designing a rectifier circuit, you must make sure that the diode that you are using, if it's a half wave, must be greater. It must have a reverse bias greater than the maximum voltage that will appear across it. So we use a special diode. There is a special diode for rectification we call the 1N4007. That one, it has a maximum reverse of 1000 volts. So when it's having a maximum reverse of 1000 volts, this 325 is way lower than it. So the diode never breaks down and is able to function as the rectifier that we want it to function as. Please, do we understand?
Yes, sir.
Great. 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 That's excellent. Now, when you do the math, so see something here. We said that when a diode is conducting, it is having, it latches 0.7. So if here is 325, the peak of the output will be V peak minus 0.7 volts. But since this is negligible, usually we just discard it. But every time the voltage at the output is lesser by 0.7 because it is a diode, because it's a silicon diode. Now, there are two things that you need to know, two equations you need to know. So when you look at this wave, the input wave, do you think this input wave signal and this output wave signal, they'll carry the same amount of electricity? Will they carry the same amount of electricity?
No.
No. So there is a difference. Now, and the formula is in your handout. You can refer to it. If you rectify a half wave, the average value of DC that you get is equal to V peak
It's on pi.
over pi. V peak over pi. Over pi for a half wave. So V peak over pi. So let's take example 4.5. Find the average voltage of the half wave signal below. So the average voltage of the half wave signal, and he showed us a half wave signal of, somebody said the original version of the book is so colorful. I want the original version. I don't want black and white. Those of you that want special prints, please, you can come and pay another money and we will print special ones for you. But that one is going to be 500 cedis. So.
You like
Somebody's
money.
laughing. Is that what?
We like this
You
one.
like money.
I like money. Eh? Oh, one of your classmates told me to buy a car, so I need to buy a car.
Wow.
Oh, okay, great. So this is the waveform. If you look at this waveform, what is the V peak? V peak is
50V.
what?
50.
50V. That means VDC will be equal to what? 50 over pi. And what do you get?
50.
15.915.
92 volts.
15.92.
915.
Great. That means that if you are connecting any device to this signal, you are going to get a voltage of 15. It's actually equivalent to a DC wave of 15. That's a VRMS. It's actually equivalent to a DC wave of 15.92%. That means that on the average, if you find, so V peak, if we say that VDC, if you say VDC is equal to V peak over pi, it means that VDC is 31.8% of V peak. If you're doing a half wave filtering, that means in half wave filtering, you lose about 70, 79, or let's say 78. You lose about 78% of the wave. You're not able to capture 78% of the wave. And that is not efficient at all.
68 or
Sorry, 68%. You lose about 68%. Oh, yeah, 68%, sorry. You lose about 68% of the wave. And you're not able to capture 68% of the wave. So it's not efficient at all. Please, is that right?
Yes, sir.
Great. Now, let's look at the second question, which is very important. Now, this is the thing. Because we don't have, let's say that. So because the 50 volt, that's the 7001, the 1N4001, which is a signal diode. So we call those ones a signal diode because they can withstand very few voltage. The maximum VBR is 50 volt. Now let's say that you have a 50 volt, or you have a diode that has a lesser VBR. Then can you still use it to rectify, or do you need to get a bigger one so that you can rectify? So this is one question we face in design problems. Why? Because these 1N4007, they are expensive. They are very expensive. They are expensive more than the 1N4001. So what do we do? What we do is this: we use a transformer. Transformers are cheaper. Then this transformer here will step the voltage down to the rating of the VBR rating of the IN4002. So that's how engineers cut cost. So we cut cost by using a transformer. Now, when we put a transformer here, this is a 2-to-1 ratio. That means that if the maximum voltage here is 170 V, then what will be the peak at the secondary? Peak at the secondary will be what? So 2-to-1, right?
Yeah,
That means that, good. That means that the voltage at the secondary will be what? 1 over what?
N.
1 over N, or 1 over 2 times 170. And what would that be? It will be equal to what?
85.
85 volts. So let's say this guy has a VBR max of 100 volts. You see that 85 volts can simply work with it.
Yeah.
Please, we understand. Please, do we understand?
Yes, sir.
Yes, sir.
Great. Excellent. Now, when we get a V peak of the secondary, it is this V peak that is going to be rectified by this to give us the voltage of the output. Please, we understand.
Yes, sir.
But remember that I said the V peak, because the diode will latch 0.7, we can say that for the VDC out, is going to be 85 minus 0.7
7V.
over pi. Please, is that right? So you see, I told you that the diode always latches 0.7. Whatever input you give, it will take 0.7 and then the rest is what will be available at the output.
Yes, sir.
Please, we understand. Yes.
No,
Hello, I'm saying that. You see, I told you that if we have a diode here, like this, then this is input and this is output. If I put 5 or 1 here, this guy will keep 0.7. So what do I get at the output? 0.3. Is that right?
0.5.
yeah.
If I put in 10, this guy would latch 0.7. So what will I get at the output?
9.3.
9.3. So if I give it 85 at the input here, so here from the mains here is 85 because it steps it down to 2. The input will be 85. What will be the output here?
84.3.
84.3. That will be the maximum that. Yes, that will be the maximum that the resistor would want. So that will be the maximum
Voltage. DC output.
voltage at the output. So V out peak. Please, we understand.
Yes, sir.
Yes, sir.
Great. Then we would calculate the V average DC. Please, the average DC, we use the peak without taking the 0.7. Please take note of that. I was saying you take the 0.7, but you don't take the 0.7. You maintain the peak. The reason is that when we were doing the math, we didn't factor in that 0.7. And besides, the peak available at the input is not, minus 0.7. So you can't use that one, but you have to actually use a peak that is available at the input. So the peak available at the input is what? 85 over pi. And what do we get for the average? We get what?
27.05.
27.05 volts. Great. So when you get this question in your exams and your midterm, you should be able to do it. Then
Sure.
the next part is the full wave. Full wave. So you see that the half wave gives you only 31.8%. 60.
Sir, please, I have a question.
60. Yes, please, yes.
Okay, when you were talking, I forgot to ask. When you just mentioned it, and my mind clicked. That's why I'm coming to ask again.
That's okay.
Question is, for the applied forward voltage, must the width of the depletion region reduce?
Come again. You said for the applied forward voltage.
Yes. Must the width of the depletion region reduce? Does it have to reduce the width of the depletion region?
Oh,
yes.
Great. So that is so the width of the depletion region can be reduced. In fact, you see, I explained earlier that when we say a diode has conducted, it doesn't mean there is no more a depletion region. A depletion region is always established in a diode that is healthy. That is how come when you take your voltage out, when you take your voltage back, it can still reform. It can reorganize itself and then form back again. But so the depletion region is always there, even in the forward bias mode is always there. And I told you that 0.7 volts that it latches is used to actually maintain and sustain that depletion region. Is that right? Please, you understand?
Yes, I understand. Thank you.
Great. So the depletion region will always be there. It won't go anywhere. It goes away when you exceed the breakdown voltage. Then that way it's not able to come back again. Then it stays there. It gets spoiled totally. So the depletion region just gets destroyed when you are able to break it down. Please, do we understand?
Yes, sir.
Great. Now let's capture more. So we want to capture more. We want to capture more energy. We want to get all the two waves. You see, right now we have half wave. We want to get all the two waves rectified. So how do we do that? We use a bridge, a rectification bridge. But this thing, you did it in senior high school. So why am I wasting my time? Shouldn't we skip it?
We didn't understand.
Ah, how?
Yeah. You have to teach again.
Assembly critical. So let's look at this bridge. Look at how it works. So in this bridge, Paul said I should skip. Yeah, hit a bump, hit a bump.
Majority.
Come again, I didn't hear you.
Sir, tell him to close his ears. You will let
I said,
okay.
nah, you're critical. Wow, come on,
Hey,
too
Masawe,
let's let's do our work. Okay,
You are coming to swallow him.
let's look at how this thing works. So when the wave is in the positive side here, when we have the positive side here, it looks like this. The circuit looks like this. Let me copy this image. I didn't want to copy it. So I'm giving you a taste of how the handout looks like in the real colored form. So there you'll be testy. We will need be who can answer. Nice Okay, guys. So this one is positive. Look at what happens. Forget about this one. One is positive. Which of these diodes should connect when it's positive? You just look at it. D1, D2. Which of them becomes D1, D2, D3, D4? Which of them becomes what? You can look in your handout, but I'll challenge you to not look at it. If this side here, this top part here is positive, and this side here is negative, which of these two diodes, D1 and D2, is forward biased? And so which ones will connect?
The positive side.
So D1 and D2, between D1 and D2, which one will be forward biased? So
D2.
it looks like this.
D2
It looks like
before.
this. D2 will be forward biased. Exactly. So let me draw it this way, so you see it well. And here is positive. So this is D2 and D1. Please, you understand?
Yes.
Which
Yes.
one is forward biased?
D2.
D2. So D1
Yes.
would not conduct. Is that right? When voltage is positive. Please, do we understand?
Yes.
So this guy will not conduct. This guy is off. Is in reverse bias mode. Then this one conducts. So this one conducts current. So current starts flowing. then it starts coming here. But when we reach here, this guy, is he reverse bias or forward bias? Look at it. Here is positive because this one is connected. So here is conducted. Because it's connected, the voltage that we have at the input, VM, here, right? This guy will take his 0.7 out and we have VM minus 0.7 here. So this one is over here. Will this guy conduct? Is it forward bias? Would D4 be forward biased?
It won't
No.
conduct.
No, sir.
No, it won't be forward bias. This is reverse bias. So that guy will not. So current wouldn't flow there. It will come and start flowing through this one. Then it comes, when it gets here, the voltage, this one is having a resistance. So it will take its own out of it. So we have Vm minus 0.7 minus what goes through the load. And so here will be positive, still positive. Is that right?
Yes, sir.
But if you look at this diode, is it forward biased or reverse biased? D3.
Forward.
Forward.
It's forward because the anode is greater than the what? Cathode. Is that right?
Okay.
Please, do we understand?
Yes, sir.
Yes, sir.
Yes. So that one too will conduct. So this one will not conduct. So this one too will conduct. Then the current flows back into the circuit. So in the forward direction, the current goes this way, like this, comes here, pass through this, passes here, then goes back. Please, do we understand?
Yes, sir.
Great. In the reverse bias, so this is how it looks like this. But then observe that in this case, the maximum at the output, that we are getting is going to be equivalent to Vm minus 1.4. Sorry, 1.4 volts. Because two diodes conducted and each of them took their 0.4 out of it. So we are going to get Vm minus 1.4. Please, do we understand?
Yeah.
Hello?
Hi.
Please, do we understand?
Yes, sir.
Great. So in this case, we take the minus from it, then we will get what we have. Please, are we good? All right, great. Now let's look at the other cycle. Let's look at the other cycle. In the other cycle, when the voltage, where is this other cycle? Let me take the clean one. Then we go again for the reverse cycle. This guy send me pisca. Straight now I name pisca. Hey. Joy crown. Can't say some no aha. Bruh. So let's look at this. Now let's look at the negative cycle. In the negative cycle, look at what happens. It's the negative part that is coming. This part. So here is like this. But here is positive. So what happens?
Yes.
In the negative side, here will be negative. The voltage here will be negative. Is that right? Then the voltage here will be what? Positive.
Positive.
So what happens here? What happens is that D2, because here is negative and here is positive, D2 will know what? Conduct.
Yeah.
Is that right?
Yes, sir.
So this one will conduct. Like this.
Default
We came here. So we have Vm minus 0.7. Someone is giving me feedback. Can you kindly turn it off? Then we have the current going through this, then going through the load, and coming here. So when it gets here, now look at what happens here. When it gets to this point, here is negative. This part is negative, and this part is positive. Is D3 forward biased?
No.
No, it's reverse biased. So that one
Oh.
too will not conduct.
Um,
So it comes through this and come here. When we get here, here is minus and here is plus. So you see, is it forward biased or reverse biased?
Forward.
Forward biased. We can now go through it. Then we come to. Please, do we understand?
yes.
Yeah.
Uh-huh. So you see that in both cycles, we've still been able to pass current through the load. In the first cycle, the load entered this way. In the second cycle, the load entered this way. In all cycles, we've been able to pass current through the load. And so our work is done. So we don't take half, we took both of the loads. And so we consider our work to be completely done. Please, is that right?
Okay.
So for the full wave rectification, the VDC average is equal to twice of the V peak
Yeah.
over pi, because we've taken both of them. Right, so we get it 2 times V peak over pi. In your exams, you get some of these questions. Oh, hey, it's your life. So take it serious. Yeah, take it very serious. Now, one other thing you should observe is that the V peak of the rectified is equal to V peak minus 1.4 volts, because 2 diodes conduct. Is that right? So the V peak will not be the same. Please, do we understand?
Yes, sir.
Great. Now that means that, so the output of the full wave rectifier will now look exactly like this. It will look like this. So some of my students have been asking me why I like Teams, and this is why I like Teams, because of the Microsoft ecosystem. You can flawlessly use both an app and your laptop together easily. So this will be the output. You have all the 2 of them there. And the VDC is going to be this. Please, do we understand?
Yes,
Now,
sir.
that means that what will be the frequency of this wave? Because this is a
100.
full cycle. 100. This
Yes, sir.
becomes, yes, 100 hertz. So that means it's having more ripples. And we don't really like that. Because if the devices are rated for 50 hertz and then you're giving us 100 hertz, that's a lot. And we don't really like that. So we need to filter it out. So the next section, which will be the last section for today, will be
Capacity.
the capacitor filters, the capacitor smoothing filters. Then I think the rest, you go and read it. We won't come back to this topic again before your midterm. So the rest will be the capacitor filters. But if you'll be writing your midterm on Friday, on Monday, we would go on to chapter 5, but chapter 5 will not be part of your midterm. Your midterm will just be from chapter 1 to chapter 0 to chapter 4. Is that right? So take note of that.
Okay.
Yes. So that is that. Now let's take one example. Let's take one practical example. A PLC, a programmable logic controller for an automated conveyor system, has an internal power supply. The mains transformer secondary delivers 12 volts RMS, right? For 1N407 407 diodes form a full wave bridge rectifier. Find the peak AC voltage from the transformer secondary. So find the peak AC voltage from the transformer secondary. Then the rectified DC voltage from the after the bridge, then the average DC voltage, then the ripple frequency, and the minimum voltage rating for the smoothing capacitor. So if you're able to design this element, you can actually build it and then use it for your PLC and it'll work. And because it's still producing the same voltage output. So let's go through it. Number one, he says that the mains transformer secondary, you know that the transformer secondary is the output, the primary is the input. Is that right? So he says the output is giving us 12 volts RMS. 12 volt RMS. If we give you 12 volt RMS, what's the maximum? Yes.
12 root 2, so 16 point.
So that with 12 root 2, that's excellent. Because if I tell you that is
16.97.
yes, so this is, let me just depict the transformer here. And he says that this output, the output here, so this is Vs is equal to 12 V RMS. So V peak at the secondary will be equal to 12 root 2. And that's equal to what? 16.97.
16.97.
Approximately what? 17 volts.
17.
So that will be the answer to A. The V peak of the secondary.
17.
What's the V peak of the secondary? Then the B is to find the V peak of the rectified DC voltage. So the rectified DC voltage looks like this. Then because it is passing through two diodes, right, the V peak of the rectified is going to be equal to 17
peak of E.
volts minus 1.4. And so we have what? 15.6 V. Yeah, 15.6 V. Then C. C is to find the average DC voltage. VDC average is equal to V peak over pi. And this is going to be equal to 17, right?
So you are doing
Yeah, sorry, 2. Yes. So 2. Thank you very much. 2. Now what do we have? 2 times V peak is what? Sorry, the formula. Yes, so that's V peak minus 2 VF. Yeah, so the formula for the V peak includes minus 2 VF. Let me be very sure if I didn't make a typo mistake. Because you guys were on my neck. So I was preparing this under hot pressure for you. So I think in solving it, I repeated the minus 2 VF. It's not right. So don't include it. It's just 2 V peak times that. So correct it in your book. So 2 V peak. V peak is 17, right? 17 V over pi. And we are going to get what? What will you get? 10.
10.825.
Yes. Great. Then the ripple frequency. The ripple frequency now becomes equivalent to what? 2 times 50 hertz, because now we have 2 waves. And that becomes 100 hertz. Is that right? Then capacitor must withstand at least 15.6 V. So here the voltage is 10. Right? 10. Sorry. The peak the peak of the output is 15.6. Is that right?
Yeah.
So a capacitor that is going to be used to rectify must withstand a minimum of 15.6 volt. Please, do we understand?
Yes,
If the
sir.
capacitor's voltage is not up to this, the capacitor will burn. So E, the V capacitor should be equal to 15.6 V. Please, do we understand?
Yes.
All right, and that's what we call the V ripple. Yeah. Now, the formula for finding the size of the capacitor to smooth it. So you see, I told you the capacitors are used to smoothing things out, right? If we add a capacitor to it, then the output becomes like this. Let me show that part for you to see. Where is that part in the circuit? That's on page 100. You go back to page 100. Then
Page 100.
page 100, yes.
Page 100.
Page 100. And you have that picture there. For that picture is so colorful in the colored version. You guys are not enjoying life.
Yeah. Yeah.
Which
But
one?
teasing us.
I have favorite if I have one. Which one?
You have what?
Which
You
picture
say you
are
have what?
you talking about?
Hello?
I said page 100.
Yeah, page 100, yes.
There.
So in page 100, you see, so when you have the half wave or the full wave like this, the filtered one looks like this. So this is how the rectifiers that we use, the rectifier circuit. This is a full rectifier circuit. So I can ask you to draw the block diagram of a rectifier circuit. And we have the connector here, transformer, rectifier, filter, regulator, and load. These are how we supply power in our system. So whenever you are building a device, then you need a power supply. These are how we design it. That's just for basics. So we need to use a capacitor to filter this thing so that we will not get a lot of ripples. Otherwise, most of our circuits will get spoiled. Now, what's the formula? The formula is in your book, right? 103. V ripple is equivalent to I load over F ripple times C. So the formula is in your book already.
Yes.
Now, when you
Yes,
make
sir.
C the subject, then you can get the ripple marks. Now, that means that if you have large C, if you have a large capacitor, then you have a very small ripple. So the ripple is like the changes. So let's say we have a voltage signal that looks like this. Then we want the ripple to now look like this. So this here, the difference is what we call the ripple. So if you want it to be small, so that it looks like this, very small, then your C must be very large. For the ripple to be small, the C must be very large. But if your C2 is large, that means that you have large inrush current. So in designing, we balance these two so that we can have an ideal inrush current and then optimum ripple. So you cannot completely take the ripple out. No matter, even if you put an infinite capacitor there, you still will get ripples. So you cannot completely take ripple out. You always will get ripples. Please, we understand.
Yes,
Hello, are we here?
Yes, sir.
Yeah.
You guys are
yes,
tired. You
sir.
want me to close the class? We will soon be closing.
Okay, sir.
So let's take the example 4.8 because you'll be getting an exam on it. And I think you can work it. These ones are not difficult. The test is
Yes,
self-explanatory.
please.
Yeah, so go and look at it and work it. Then let's quickly do the last thing for chapter 4, then we are done. Zener diodes as regulators. So Zener diodes and then regulators. So you see, if you look at this block diagram here, we have a filter. Then after we get a filter, we have a regulated voltage. So when you filter it, you always use a regulated voltage. So we have two types. It's either you buy the LM7805 or the 7812 or the 7809. The 7805 will give you 5 volts. This one will give you 12 volts. This one will give you 9 volts. These are linear regulators that we use in the industry. In fact, as part of your kit, I'm ordering the 7805 for you. Person will be a beshen and sa. Because I say kit national and sa there be bonnie. So I'm ordering the small voltage. I'm not ordering the big one. The small voltage. So you will not hurt yourself. But then one day if you're designing your own circuit, I want you to be aware that these are the regulators you have. Now when you give this ripple input to it, if you give a ripple input to it like this, to an A7805, the output is fixed. It doesn't change at all. Then you now have a pure DC out of this. So that is how we build power systems for you, for basic electronic, for mechanical engineers. That's how we build power systems. So you just get a regulator. Now there are two options. It's either you are using a linear regulator or you are using a Zener diode for the regulation. That's why we have a linear regulator or a Zener regulator. Why do we like Zener regulator? Recall that I told you that if a diode enters the breakdown mode, it's never able to recover from it. It stays there permanently. Now, if you take a normal diode, I've told you that if you take a normal diode, if it enters the breakdown mode, this is how it looks like. It stays in the Zener region permanently in free hole, and voltage keeps increasing as long as you increase current, right? It keeps increasing. That's the real diodes, the real behavior of a real diode. But the Zener diode, what we do is that in the Zener diode, somebody is asking me if I can share the video right after class. Please, I will try my very best and do that. Usually it's because of the network. So it makes it very hard. Right after class, when I try posting, the network is very bad. So I would have to wait till evening, then I can post. But I'll try right after class and see that it works. So let's see how it works here. You're welcome. Someone said thank you. So you're welcome. I'm glad you did. Thanks for asking the question too. Okay, great. So this is how the Zener diodes behave like. Let's summarize it quick. Then when you're reading it in the handout, you can easily understand. Otherwise, when you read it, you will not understand. Okay. So this is how the Zener diode looks like. So whilst in the real world, we say that the diode behaves like this. So in the real world, we say the diode behaves like this. For the Zener diode, we just make sure that it behaves like this. Straight. It doesn't change. It doesn't change. It behaves like this. So over here is the typical behavior of, which is 0.7 volt here. But then in this mode, it stays fixed. And we make sure that it stays like that. We've doped it out. So they've doped it and they've beat it down so that regardless of how the power changes, the voltage is fixed. It keeps on going. That's how the ideal Zener diode must behave. But to be honest with you, it doesn't behave like that. But to make life simple for us, we assume that even in the real world, it still behaves like a Zener diode. In fact, that is why we have special linear regulators there as alternative to the Zener diode regulators, because you don't know how it's going to behave in the real world. So how does this thing work? So that means that Zener diodes are always connected in the reverse mode, right? So they are connected in the reverse bias mode. So Zener diodes are not connected in forward bias mode. They are always connected in reverse bias mode. So take note of that. So that's where it can get a little tricky. In your exams, I can just put it there because when you say tricky, a bit tricky. You know, I'll just come to you when you're writing basic electronics. I'll just come and laugh at you, and I will come back. You know, you see. So take note of this. It's very, very important. So this is what it means. Let me give you the circuit here. Where did I put this one? That means that if I connect any device across a Zener diode, if I connect any device across a Zener diode, then, okay, great. So here you have the diagram like this. Okay, so this is it. People are having very bad network. You see, my students are tired, so I'm on Kasabio. Why? Scan starting bar, on Kaiser now, bro. You even forgot. You even forget. So look at it. So we connect Zener diodes in the reverse mode. So you see that we connect it in the reverse. And another note is that to differentiate between Zener diodes and the normal diodes, we use the Z here. So this Z, somebody said this is not how we write Z. You Mate. So we use this symbol for Zener diodes, and it's always connected in reverse. Now, because of this diagram, when you connect it in reverse, what it means is that it will latch this voltage, this VZ. It will latch it here. So any device you connect to it, it will be in parallel to that Zener diode, and it will latch that VC. So that device too will get that constant voltage of VC. And mind you that I said for Zener diodes, we make sure that it stays there, it doesn't change. That means that as long as you operate that device, regardless of the changing VI here, this guy will make sure this one is getting VZ fixed without changing. Please, we understand. Hello?
No, sir.
Yes,
No,
yes,
sir.
sir, please.
Yes, sir.
You don't understand.
Sir,
We
please
do.
go over.
Okay, let me go over this. Let me go over this again. So we said that a Zener diode operates in the breakdown region. So when we connect it, so we always connect it in a reverse. When we connect it in a reverse mode, every Zener diode is having its breakdown voltage, its Zener voltage, Zener rating. So when we say that Zener diode, so they have specific ratings, right? We have the 3.3, we have the 4.7, we have the 5.1. These are the common values you get on the market, 5.1 V. That means that when you connect any voltage to it, if it's a 3.3 volt Zener diode, or let me start from a 5.1. If it's a 5.1 Zener diode, then you connect it to a 3.3 volt. What happens is that as long as you've not gotten to that VZ of 3.3, sorry, so it's a 5.1, yes, 5.1. So as long as 5.1 and you connect it to 3.3, as long as you are not there yet, you won't see anything. Everything is zero. It's not connecting. It won't work. It will not conduct. It's zero. Nothing works. Everything is zero. Voltage is zero. Current is zero. It won't work, right? Because you haven't gotten to it. But the moment you increase your supply up to 5.1, then it starts to conduct. Then when it conducts, remember that I told you that it latches 5.1. So the excess is what goes somewhere. So if you have a resistor here, this guy will latch 5.1, then the excess will come across this resistor. Please, you understand? So if we have if you have 5.1 here, then the excess will come. Now, because this is 5.1, if this guy conducts, there will be no voltage across this resistor. That means that no current will be flowing. That means this diode too will not work. So let me use 6 volts for the analysis. 6.0 for the analysis. If you connect 6.0 volts to it, when this guy, the moment you connect 6.0 volts, 6.0 volts is more than the 5.1. So the 5.1, this guy will connect. At 5.1, it will connect and latch there. It will stay there. If I say latch, it means it will stay there and come baby. Then the excess volt of 0.9 will appear across this resistor. Is that right? Then the 5.1 will appear across the Zener. Now, aka. Enkona nim opa raise current no go drew 100 volt. Still now 5.1 na aka. A one a bet na no matter how you raise the voltage, you can raise it to 1000, 5.1 na a bet na. All the excess will come across this resistor. So we call this the bleed resistor. Right? The bleed resistor. It bleeds the excess. It takes all the time, it takes the excess. Then all the 5.1 aka because I say that would not say. The Zener diode has poles, so it only functions in the breakdown mode. It's the moment it connects, it only it's either it is working or it's not working, and it only works when it gets its minimum Zener voltage. When the moment it gets that, you see, I was about to say when it gets when it gets that Zener it stays there. You can put 100 times that, it will still stay there. It will not increase again. But the excess will all appear across the bleeding resistor. Now, if that is the case, that means that when I connect any device or any load in parallel across that Zener diode, without nothing happening between them, we told you that in parallel, voltages are the same, isn't it? Then in series, current is the same. Power V series I. Right? So in series, current is the same. In voltage, in parallel, voltage is the same. That means that if I connect any load in parallel to that Zener, then when it starts conducting, and it stays there at that 5.1, even if the input is changing, the load will still see that constant volt of what? 5.1. And that is the advantage of the breakdown voltage of diodes. Eclipse, please, do you understand? You can give me a thumbs up. Please, we get it.
Yes, sir.
Great. So that is the Zener diode, and that is how and why we use it. That's the only way we use the Zener diode. Any question before we start solving some? We just solve one question, then the rest you go and practice on your own. You take the handouts plus a video, and then you can go and do it. Hello? Yes.
Yeah, poor network.
Okay. Oh, Charlie. Monkafra. So now there are 2 steps in designing a Zener regulator. 2 steps, 2 major steps, and you need to take note of it. The first step is to find out if the Zener diode would be biased. If the Zener diode will be biased. What do I mean by that? Let me take this first example so you will get it. Otherwise, you won't understand. This first example looks scary, but it's simple. Let me take that one so that you can understand what is going on here. Okay, so I need to solve all of these 2 examples so you understand. Copy image. Let's come here. Okay, great. All right. Okay, awesome. Now we have this, and there is something called reference voltage. Next week, when we meet on Monday, you'll understand why reference voltages are very important. So there's something called reference voltage. So this is a circuit we have. We've connected it to a source of 40 volts. Then we have this one, then we have this white LED. Then we have one Zener, and the Zener is rated 6 volts, and another Zener which is rated 3 volts, and then silicon converting. The question is asking us to find VOI and then VO, so VO1 and VO2. Is that right? For the reference. So usually that's one thing we use Zener diodes for. We use Zener diodes to provide reference, to maintain reference points for any device. Now, if this guy conducts, if it works, what will be VO1? What will it be? So we said Zener diodes, when they conduct, it maintains this 3.3 volts regardless of the changing supply. That means that here will be 3.3 plus this silicon. And silicon, if it conducts, what does it maintain?
0.7.
0.7.
0.7. So that will be 0.7 volts. And so this will be what? 4.0 volts reference. Please, do we understand?
Yes,
Yes,
sir.
please.
Great. That means VOI is 4.0. Then VO2 will be what? VO1 plus what? 6 volts. And that will be equal to what? 10. Please, do we understand?
Yes, sir.
Yeah.
Great. Great. Hello, please, are we here?
Yes, sir.
Great. That's excellent. Now, the question is asking us to determine the reference voltages in the provided by the network below, which uses a white LED. And what is the level of current through the LED and the power delivered by the supply? Great. So what's the level of current through the LED? So what is the I in the LED? So over here, how do we calculate it? I told you that I is established by the current, the resistor. Is that right? So VR over R. So we need to find VR. And VR is going to be, so here is VO, which is 10 volts. Then white is having a forward drop of 4, right? In fact, 4 or 4.1, let's use 4 volts, right? So that means that we have 40 here, 40 at the source, right? 40 at the source. Then we have 4 volts and 10 volts here. That means the voltage across all of the remaining voltage now appears across the resistor. So the voltage of the resistor will be 40 minus 10 minus 4 all over the resistance, which is 1.3 K. And this is going to be equivalent to, what will it be? Yes,
26.
26 over 1.3 K. And so what do we get?
20 milliamps.
20 milliamps. So the LED will turn on for us, and we still get the reference we need. Please, we understand.
Yes, sir.
Hello.
Hi.
Please, we understand.
Hi.
Yes, sir.
Yes, sir.
Okay, great. That's excellent. Excellent. Now we can calculate the power. We can calculate the power delivered by the supply and absorbed by each of these using the various power formulas. We know P is equal to IV is equal to I squared R and all. So we can calculate all of that. You can always do that. So that is how we solve that. Now, let's take the regulation. Let's take one question on regulation so you understand it if I bring it in the exams. So let's take this one here. Then example 4.1. So this is how the world of electronics work. And when you go to the industry, all the electronic devices you use there, these are how they work. And if you're able to understand it, you would really be able to work in the industry well. So let's analyze this circuit. We said this Zener diode is a 10 volt Zener diode. So first of all, to analyze it, you would act as if there is no Zener diode there. So you redraw the circuit without a Zener. You remove it so that you want to see. The reason why you're doing that is that we want to see if the Zener diode will conduct or it will not conduct. Because mind you, this is a voltage divider. If I just draw it without the Zener diode, then I just have a voltage divider here. So you see, when we're learning voltage divider, I was telling you that this thing is very important. See that we are using it. We will use it till the end of the course. So if you don't understand, please go and revise that part again. Then here is RL is equal to 1.2K. Now, so this is 16 volt. If this is 16 volts, then what will be RL? RL will be what? 1.2 over 2.2 times what? 16. And what do we have? Here's what we get. Hello?
The RL.
Sorry,
That is
IL.
8.77.
So VL will be 8 point what?
77.
7.
727.
Okay, so 73 V. That means that the voltage at this point is 8.73 volt. Please, you understand?
Yes, sir.
Now, we've connected a Zener diode that only conducts when the voltage is 10. So will the Zener diode conduct?
No, sir.
No. So this Zener diode will never conduct. That means for this Zener diode to conduct, what do we need? So how do we properly bias this? Right.
We increase the load resistance.
Great. That's very excellent. So it's either we will choose a higher resistance for RL or we will reduce the resistance for what? R. So that this thing will be properly biased. So let's repeat the calculation for when RL is 3. So the question said repeat part A with RL is equals to 3. So when we repeat it, what will be VL? VL will be equal to what? 3 over 4 times 16. And what will we get? Here's what do we have? 12.
12.
So 12, that means that this is another diode that needs 10. It will conduct. Is that right?
Yes, sir. Yes,
Great.
yes.
Great. And when it conducts, the moment it conducts, it will only conduct 10. So this 12 that we've calculated will not really appear at the output. The load will get only 10. Then the remaining 4 volts would appear across R. Please, do we understand?
Yeah.
Great. Then the remaining 4 volts would appear across R. So take note of that. In fact, that part is a little bit tricky, but it's because of the Zener diode. The Zener diode, no, or your star will be, if you don't give him more than it needs, it will not work. Right? So you always give him more than it needs, then it conducts. And when it conducts, you know, it will now start determining how the circuit behave. So here, this one will take, so the remaining 4 would appear. So this one will take 10 volts. Then here is 16. So here, this one will take 6 volts. So the remaining 6 will appear across the load line resistor. So here would be 6 volt, and here will be 10 volt instead of the 12 volt because of the Zener diode. So kindly take your time and then go through the handout and understand these things well, because the way it is tricky, I like it. I mean, those tricky things now me pen. Now with Timosa, now I saw a shit. So really take your time and understand, solve the questions, solve the ones behind. Then you can be able to really understand how this thing works. On that note, any question? Most of my people are crying unicorns or guys. Thank you all very much. Thank you.
The last question. The last question.
Yes.
For the full wave rectification.
Yes.
There are 4 diodes. Is it because 2 connect at a time? That's why we are when finding the average. When finding the peak, we use the average. We use 2 times the 0.7.
Oh, that's a very brilliant question. So, but you have a good observation, but it's not because of that. The reason why we use 2 is because you see in the half wave, it looks like this. There is a space here. You have this gap here.
Yeah.
But then this one in the full wave, it is 2. You get it?
Yes, sir.
Then the half wave is like this. So you see, if one of this is V peak over pi, then 2 of this will be what? 2 V peak over pi.
Okay. Thank you.
Great, you're welcome. Yes, ask your question, please, Collins.
Yeah, sir, please, I want to know, how did we get the resistance that is the 3 and the 3/2 volts? I don't understand that part.
For the Zener rectification.
Yeah, yes, please.
So the Zener rectification, the question asked that we should recalculate it using an RL of 3 k ohm.
Okay.
Yeah.
Thank you.
You're welcome. Yes, Tabitha. I like that name. That's a very nice name. Tabitha, please unmute and speak. You're on mute right now. Tabitha, please speak. Okay, Yao Kakari says, sir, please, the whole show. The whole show, I don't understand. From whatever we started talking about from 5 or what? I don't get it. Okay, if it's the whole show, you know what? I'm going to upload the video on YouTube. Just watch it again, and then you'll get the whole show. Yeah. So I'll be uploading it. I'll try uploading it right after the class, like somebody has requested. I'll just try several times so that you can just watch it right after. Yeah, great. Please, the diode needs 10 volts. Yes. So when we calculate the rectification, the resistor will bias to be 12. So initially the bias is what? Because now it's not working. So don't think too difficult about this. You see, we said that the Zener diode will conduct if only when the voltage exceeds the breakdown voltage, right? So look at how it works. when it starts from, so let's just start thinking. When we turn the device on and it starts moving from 16 volts, right? So 16 volts, it start moving from 16 volts. So it start from 0. Let's just assume that we want, so from 0, it goes to 5. When it goes to 5, still this diode is not conducting. It doesn't conduct. Does it conduct? No, it won't. It won't conduct. It's 0. So the circuit is largely like a potential divider. That's why we say when you're analyzing it, take it off. Just take it off. Don't leave it there. Just take it off. Because when it starts working, until the voltage reaches the minimum that it needs, the diode, that Zener diode, is barely there. It's not there. So just take it off. Right? Then the voltage keeps ramping up. It gets to 8. So still now is a potential divider. Then the voltage keeps ramping up and gets to 10. Then now it conducts. But in the exams, you cannot be writing that, oh, let's take it off. No, you can't do that. This is a professional field. So you can't tell me that, say, let's be taking it off. No. Taking it off, saying, right? You don't do that. So you say, okay, if we take it off and we are connecting it to 16 volts, then let's calculate the voltage that would appear across the output here using the basic voltage divider that it is. Is that right? Then when you do that calculation, you will get the voltage using those basic divider. And you find out that when the diode doesn't start conducting, the maximum voltage that will appear across RL at any point in time, assuming the diode is not there, would be 12 volts. That means that, that 12 volts is sufficient enough, it's able to bias a Zener diode, right? But the Zener diode is having a behavior that means that when the voltage gets to 10 volts, the Zener diode can bias. Then it starts working. And I've told you that when the Zener diode biases and starts working, the voltage 10, it stays there. Even if you put 20 at the input, it will still stay at 10. It stays there because I say, like, it has broken down. So it can't do anything again. It stays there. It can only function there. That's why we deliberately pick certain diodes and we deliberately break it down so we can use it that way. Then in that way, it will stay there and it will keep on regulating the loads for us. Please, we understand. So don't think so hard about it. So all the time, first of all, you take the diode out because when you start working it, it's ramping up and current is not working. So it's just not there. So we will find the maximum bias voltage that can ever appear across that diode. Then we see that, okay, that means this thing can appear across it. But once the diode start conducting, it would conduct only 10. Only 10. So here is 16 volts. Only 10 per no. Or the Bema output. So instead of 12 volts, a bare 10 volts. Then the remaining 6 will be across the resistor. So your job as an engineer is to calculate if 6 volts is appearing here, what should be the power rating of the resistor so that the resistor there will not burn? And what should be the value of the resistor so that it will properly bias this load so it will keep on functioning. So that will be your job so that the circuit will work. I hope we get it.
Yes, sir.
Great. So just go over the video again. The whole day is yours, Charlie. Enjoy. Now, a reminder on the assignment I gave for your groups. Please don't forget. Your groups must meet. You guys should learn. Go over this together as a group. Teach yourselves so that you understand and you don't forget that when you come to the exams, you just write whatever you learned in your group. It's just the same thing that you're going to get. So please,
Okay, sir.
I've
Do we
specified
have
it in the beginning of the recording. So when you go and play it back, you would have all of those information for yourself.
Okay.
Now I'm running late. I have to run into another meeting right now. So have a very, very nice day. And make sure you are safe everywhere.
Thank you, sir. Bye.
Yeah, bye.
Bye.
Bye. Nana Sewa, bye.
Bye.
Nana Osei Tutu, bye. Genevieve,
Say,
bye. Eva Genevieve, thank you very
Okay,
much. You were one
bye-bye.
of the few people that joined early. God bless you. Yes, bye.
champagne for
Okay, bye-bye.
Bye. Yes,
say
Danso.
champagne for
Danso, you have something to say?
say Mr. Champ class in pain for in the man before you.
What's it?
Check in pain for no before you pay.
I'm gonna be there.
Check class in pain no before you pay.
Yeah. Hey, Nana, my friend, Nana will say it too. Pacho bio. Na afia se wa me pacho. Wadarema. Uko to dream na mikita bye. I am friend me and him. Okay. All right. Yes, bye.